Hi guys, so I'm going to get straight into it. So we're going to be covering ionic and covalent bonds and also polarity. So starting with ionic and covalent, we have already discussed this in class previously, and now we're just going to review it because it is going to be discussed in this next unit. So with ionic compounds, remember, ionic compounds, they are when you have a metal and a non-metal. And covalent is when you have two nonmetals. So remember, a metal is called a cation and a non-metal is called an anion. And here in ionic bonding, the electrons are being stolen from the sodium ion to the chlorine ion. And then covalent, they are sharing. So first, let's go ahead and talk about where in our periodic table are our metals and nonmetals. So all our metals, they are going to be underneath this staircase. Does everyone see the staircase? So all of this, all of these are metals. And then your nonmetals will be the ones to the right of the staircase. So these are the main two that we're going to be focused on. So our metals and nonmetals. So remember, ionic, whenever we have an ionic compound, we have a metal plus another nonmetal. And here they would steal the electrons, they would take them away. Now in covalent compounds, we have two nonmetals. So a nonmetal plus another nonmetal. So we would have two from this side. When you have an ionic, you have one from your left and one from your right. So let's go ahead and begin to talk about molecular polarity. So polarity in molecules determine whether or not electrons in that molecule are shared equally. So remember, if they are asymmetrical, meaning they don't have symmetry, like maybe one's pulls in those electrons a little bit more than the other, maybe even just like the angles of the bond are not evenly distributed, then it would be considered polar. If there is symmetry and there are symmetrical, then they would be considered non-polar, the molecules. So how do we determine whether we have a polar or non-polar molecule? Well, one of the things that we are definitely going to have to utilize is the electronegativity chart. So in the electronegativity chart, you're going to have all the all the atoms with their electronegativity numbers. And if you remember, fluorine had the greatest electronegativity. Remember, fluorine is the most electronegative atom on there, and that one has a 4.0. So you would basically, depending on which other elements are with, when you subtract them, if you get a number that is between 0 and 0.4, it will be considered a non-polar bond. But if you get one from 0.5 to 1.7, it will be considered polar. If you get one and it is greater than 1.7, that would mean it is ionic or polar ionic. So when we have non-polar molecules, that means there are no unbonded electrons. That means all the electrons have a pair. Each bond in the molecule has the same polarity, meaning no unbonded electron pairs on the central atom. So let's think of really quick like NF3. this would not be considered polar, or this would not be considered non-polar, sorry, because it has lone pairs on the central atom. Because it does have the lone pair on the central atom, that means that it will, in fact, be polar. But if you look at, for instance, carbon tetrafluoride, now carbon does not have any unbonded electron pairs on the central atom. That means they're all paired up. And there is no net dipole moment. All moments cancel out. So for instance, there is no overall net dipole. Remember, and I told you guys to draw an arrow toward the more electronegative atom, and we said fluorine is the most electronegative. So that means we would draw our arrows pointing towards fluorine. And then remember, we draw a little tail here. That shows us that we have a positive end over here toward the nitrogen. So we would go ahead and draw them for all of them. Now, if you look here on the carbon tetrafluoride, and use red to cancel them out, this down one would cancel out with this up one. This left one would cancel out with this right one. But here you would have these two cancel out, but nothing is canceling out this one that's going down. So for nitrogen trifluoride, you would have an overall net dipole moment going down, which means this one is polar. But because this one, it all cancels out, there's no overall net dipoles, there's no lone pairs on the central atom, this one would be considered non-polar. So, like I said, the molecule is considered polar if there is a net dipole moment. That means if there is the leftover arrow on it, so like with the NF3 nitrogen trifluoride, there was. Each bond in the molecule is nonpolar, but there are unbonded electron pairs on the central atom. Now, let me go ahead and get you an example for that one. Let's say we have NBr3. Okay, so nitrogen, the electronegativity value is 3.0. 3.0. And bromine is 2.8. Now, when we draw them out, right here, that means we have to draw 3 bromines. There you go. I'm going to go ahead and draw the electrons real quick. Now, when we look at the electronegativity values, nitrogen is a 3.0. Bromine is 2.8. When we subtract those values, we get 0.2. Remember, it has to be 0.5 or greater to be considered polar. So the bonds from nitrogen to bromine, the bonds are actually non-polar. But because it has this lone pair on the central atom, would make it a polar molecule, but it has non-polar bonds. So bonds in the molecule have different polarities and unbonded electron pairs on the central atom. So that's what we're talking about here. So for dipole moment, it is the direction of the polar bond in the molecule. Arrow points toward the more electronegative atom. So for instance, between hydrogen and chlorine, you have to look at the electronegativity values, or a quick hint is to determine which one is closest to fluorine. Remember, fluorine is the most electronegative. So chlorine is definitely a lot closer. So we would draw our dipole moment pointing towards chlorine, leaving hydrogen slightly positive. And we would do the symbol delta. So it's slightly positive on the hydrogen, and it will be slightly negative on the chlorine. And our dipole moment goes towards the chlorine because it is a more electronegative. So nonpolar molecules, dipole moments are symmetrical and cancel out. So let's look at BF3. Boron does not have any extra lone pairs on the central atom. Think of it as if they were all pointing out this way. They were all pointing out, and they're all pointing, like pulling outwards toward the fluorines with the same amount of electronegativity. So not one side wants more than the other. So because this is symmetrical, it is considered non-polar. So for polar molecules, the dipole moments are asymmetrical and don't cancel out. So remember, asymmetrical means not symmetrical. So if we look at the molecule, it would indeed have a dipole moment. So between hydrogen and oxygen, we would draw our dipoles pointing toward the oxygen because oxygen is more electronegative than hydrogen. So we're going to leave the slightly positive tails on the hydrogens, and we can show this by putting lowercase delta plus, which means partial positive charge, and that means our oxygen is partially negative. It's not an A, it's like a S connected at the end. So these two don't cancel out. In fact, they are going in one direction, which is upward. So our overall net dipole would be going up. So this is a polar molecule. So determining molecular polarity, it depends on the dipole moment and the molecule shape, which we have already previously covered shapes in our class on how we would determine what they are. But even then you can kind of tell just by the way they look that it's not symmetrical. As long as they are pretty even, then you can consider it nonpolar, at least the molecule. But if they are not symmetrical, they're asymmetrical, they're more than likely polar. So the polar bonds versus polar molecules. Now this is where you guys have to be very close attention to. Remember, bonds are just like the line from, let's say water. This is a polar bond. It's going from H to O. But the polar molecule is the entire water molecule. And we said the overall net dipole would go up. So those are two different things. The bond, it's just like one O to H, where the molecule is the entire thing. So the effect of polar bonds on the polarity entirely depend on the molecule. So for instance, carbon dioxide has two polar bonds, but the entire molecule is considered nonpolar. And the reason why, it's because here you have your carbon dioxide on the bottom, and yes, we would draw our dipole. So from the bond from C to O, that is polar. From just one C to one O, we have a polar bond here. But because of the other bond, they cancel each other out. They're pulling with the same amount of force on each side. So because it is symmetrical, they will cancel out. So polar molecules, the effect of polar bonds on the polarity of the entire molecule depends on the molecular shape. So that's one that we discussed, how water has two polar bonds and is a bent shape. The highly electronegative oxygen pulls the electrons away from the hydrogen, so it's very, very polar. So I kind of already showed you this one. So from O to H is a polar bond, but with the entire molecule, it would have an overall net dipole going up. And water is very electronegative. The oxygen is pulling those electrons toward it. So if you were to think of like a cloud, you know how like this one has the 6 here? This electron would be a lot closer to the to the oxygens compared to the hydrogen. Instead of being down here, it's slightly pulled toward the oxygen because of how electronegative oxygen is. Now, how do we determine molecular polarity? So how do we know if the molecule is polar? Well, we have to look at the shape. If the shape is asymmetrical, meaning does not have symmetry, maybe one's out of place, or the parts don't all cancel out, or maybe they even have lone pairs in the central atom, we would kind of know that it's a polar molecule. Another thing is to see if they are asymmetrical atoms, meaning where one doesn't cancel out. So for instance, let's look at this one. Remember, carbon is in the center. We're looking at CHCl3. We have this hydrogen up here. This is the only one that does not belong. So for instance, if let's say this was chlorine, this chlorine can cancel out the chlorine on the bottom. The left chlorine can cancel out the right chlorine. The top chlorine can cancel out the bottom chlorine. But because here we know our dipoles go from carbon to chlorine, and the reason why I know it goes pointing towards chlorine, because chlorine's a little bit more electronegative than carbon, because chlorine is closest to fluorine. I know, sorry, they're all sound the same. But carbon to chlorine, we would again draw our dipole, and from carbon to chlorine. But between carbon and hydrogen, carbon is actually closer to fluorine than hydrogen. So carbon is more electronegative, meaning it wants more of the electrons compared to hydrogen. So if this was a non-polar molecule, our dipole would be pointing up. But because this is a polar molecule, our hydrogen is what makes it uneven. So our dipole actually points downwards, leaving it slightly positive here at the hydrogen. So let's think about them canceling out. All these three are going down, and this one is also going down. Nothing is canceling out here. So they're going to have an overall net dipole of down. And well, that's it for this lesson. You can later on view the lesson on lattice energy. That will be our next lesson coming up. Have a good day, guys.